My name is Josh Ridge, and I'll be doing my 6-minute talk on hot water pressure washers. So here's some of the applications of a hot water pressure washer. The past few years, I've gone into commercial restaurants and cleaned the ventilation hoods in both restaurants and casinos. So hot water is very essential to remove this grease from the ventilation hoods, the ducts, and the fire suppression systems. On the right, that is a picture of one of the ducts of an El Paso restaurant. It is pretty disgusting, and it's about a year of not getting it cleaned. So we need very hot water to remove this properly. So this is the machine that I use. Some of the specs, it's 8 gallons a minute, 3,000 PSI. It does have a 2,900 watt generator with a diesel burner, so that's kind of produces the heat. And it produces 513,000 BTUs per hour of energy. So that's about 150 kilowatt burner. So all of this allows for a 150 degree temperature rise above ambient. So the heating coil has a heat exchanger at 31 right here. This is the heating coil. Water is going to enter on the right side of the machine about here. It's going to wrap through the 1/2 inch 80 Schedule 80 steel coil, and it's going to wrap through there. And then on the exit temperature, it's going to be super hot. So here we have the fuel source, and yeah, so basically it's like a heat exchanger. So the heat transfer path, it goes from convection from the flaming gases to the steel coil. We then have conduction from the outer wall of the Schedule 80 steel coil to the inner wall. And then we'll have convection again from the inner pipe wall to the water itself. And so all of this creates a large increase in exit temperature. Okay, so here is some calculations we could use. We could do the energy balance at the top, where you can say that our burner produces 150 kilowatts of power. The mass flow rate from the 8 gallons per minute is about 0.49 kilograms a second. Finding our delta T to be 132 degrees Fahrenheit, and an inlet temperature of 75 degrees, we can say that the outlet temperature would get to 207 degrees Fahrenheit. So this doesn't account for some losses and a lot of other factors. I mean, if I put in 32 degrees Fahrenheit water, it's still going to get close to that 200 degrees, so it's not completely accurate. We could do a more in-depth thing that we've learned in heat transfer, where we can find the overall heat transfer coefficient, which is at U. This is found from like a resistance network of the convection heat transfer between the burner and then the coil, and then from the coil to the water itself. So I can find our UA, and then use the log mean temperature difference to then find that temperature at the outlet. So there's a lot of factors that go into it. Finding all the H values. I don't know a lot of the things, like I don't know the temperature or the flow that the actual burner is producing. So it's not able to figure that out, but I guess if you got like a lab, you could probably figure this out. And in conclusion, the heating coil behaves like a compact heat exchanger, and then through that, heat moves through convection to conduction, back to convection. Internal convection modeled using the Lenski correlation, so that's what we can use for the internal flow if I was going to actually find the internal heat transfer coefficient. And then the coil wall resistance plus the gas water convection, all of that gives us that total heat transfer coefficient U. And then the outer, based off of this, the outlet water temperature predicted matches what the MIDM manuals said, so that's accurate. And the heat transfer theory directly connects to a tool that we see in the real world. So these are my sources, and that is all. Any questions?